In lecture 28 today, we've got 3 main things to do, spread over 2 parts of the lecture. The first thing I want to do, I've got a bunch of slides, 5 slides or so, that you probably should not take notes on. Talking about modeling the US population, as I promised. So that's what I was doing yesterday, is I was trying to model the US population. It was a lot of fun for me, and I was feeling God's pleasure, as I was mentioning to you before we started the video here, of just enjoying math and its usefulness. So I want to share that. I also want to start talking about section 3.10 again some more. We've touched on it a little bit, but I want to get into more detail. Talk about something called the mean value theorem. You really can't talk about calculus 1 without talking about mean value theorem and its consequences. That'll carry over to lecture B. And then we're going to get into parametric equations and parametric curves, the content of section 4.8. Those equations and those curves will model motion for us. That'll be our main application. And that's going to be the second to last main application for the course. The very last main application for the course is going to be, well, I guess it's maybe 2 more applications. Rates and flow rates will be one other application we get into it, as well as one more. Data modeling with what I call density curves. That will be the last topic. When we get into integration, starting on Friday. So what is this model of the US population that I was attempting to make? It's a logistic model, so it's based on that differential equation. And I had some data. This is data analysis. It's part of data science. Here are the data about the population of the United States and millions of people every 10 years since 1790. You know the US wasn't technically what it is today in 1776, right? Hope you know that. Even though that's technically when we say our nation was founded. We didn't have our structure of government until 1787, 11 years later. That was just the Declaration of Independence. We still had to beat the Brits in the Revolutionary War. That didn't happen until, I don't know, 4 or 5 years after 1776. 1787, we set up our Constitution, we set up our form of government. And in 1790, that was when the first census was done. So that's year 0, so this is 1790. The population of the US was 3.9 million people. 10 years later, in 1800, it was 5.3 million people. And it goes up. The year 1800 would be 110 years, 1900 would be 110 years after 1790, right there. This is the year 1900, 76 million. In this region here was when World War I happened. World War II would be about 150 years after 1790, 132 million people. And this was 1950 here, 60, 70. I was born in 1968, so I was born right about when the population of 200 million people. So that was 70, 80, 90, 2000, 2010 is 220 years after 1790. It was 309 million people. Question is, can we apply the logistic model? Can we, for example, figure out the carrying capacity of the United States from these data? So I tried. I'm saying we can try here, but our or my initial attempt will not be as successful as we or I might hope. Okay, I was doing this, so I guess I shouldn't be saying I, but I'm trying to bring us all into this. Okay? So how did I do it? How did I try to analyze this model? Here's the differential equation again. Right? That's the same differential equation I've written down before. dp dt is k times p times, in parentheses, 1 minus p over L, where L is the carrying capacity. That's the thing I'm trying to find here. K is this growth rate, essentially. It's the growth rate when the population is small. We've already had Mathematica find a solution to that, and we made some graphs last time in the slope field. This equation is equivalent to another equation. I could take this equation and divide both sides by p. If I do, I get this equation. What's the benefit of writing it that way? Well, what it's saying is the instantaneous relative rate of change is a linear function of p. Do you remember we talked about instantaneous relative rate of change a couple weeks ago, I think? I don't remember if it was before exam 2 or not. I think it probably was. Where you take the derivative and divide by the population itself in this case. It's a percent rate of change, instantaneous at any moment in time. It's a linear function of p. So maybe, if I could estimate the values of these things, I could try to fit it with a straight line. It's got a negative slope, and that's what I did. If we can model the instantaneous relative rates of change as a linear function of p with a negative slope, then we could, based on that straight line, figure out k, and then figure out k over L, and therefore L, the carrying factor. How do you compute values of these things? You got to look at that data on the previous slide. For example, 3.9 was the population of the US at time 0, the year 1790. 5.3 million was the population 10 years later, in the year 1800. 10 years elapsed from 1790 to 1800. Population grew from the year 1790, t equals 0, to the year 1800, t equals 10. It grew from 3.9 million up to some other value that's 5.3 million. Okay. The scale is not accurate. That's the basic idea of it. That difference, 5.3 minus 3.9, is the distance between these. The growth amount was 1.4 million. 1.4 million more people in 1800 than there were in 1790. Over 10 years elapsed, this is a rise over run, it's a slope. Really a secant line instead of a tangent line, but it can approximate the slope. It's really computing that, the slope of this line, as an approximation to the slope of this line. That's a secant line, that's a tangent line. And then I could divide by that by p, the initial population of 3.9, to get an approximate percent rate of growth. That's estimating this instantaneous relative rate of growth as a percent. About 3.59% per year. That's from t equals 0 to t equals 10. What about t equals 10 and t equals 20? Then the population grows from 5.3 million to 7.2 million. 1.9 more million people in the year 1810 than we were in the year 1800. Divide by the change in time, 10 again, and you get this rate of change. And then this corresponding relative rate of change. Emphasis on the word relative, this is a percent. And I can keep going. And I did it. I got Mathematica to do the calculations for me. I calculated dp dt divided by p, the instantaneous relative rate of growth, approximately, as these percentages. The main thing that stands out, if you look at over those green numbers, is they're going down in general, right? They're getting smaller and smaller over time. You may have heard that birth rates, for example, are declining over the years, and that's kind of reflecting the fact that birth rates are declining. The percent rate of change is going down over time. These are not times in blue, those are populations, because I want to plot dp dt over p versus p. P is going to be on the horizontal axis, and dp dt over p is going to be on the vertical axis. Kind of a strange thing to do, but it is certainly something that you can do. This does correspond to t equals 0. This is t equals 80, which is 1870. This is t is 160, which is the year 1950, just for frame of reference. And this is 1960, 70, 80, 90, 2000. I did not do an estimate for 2010, though I probably could have. I could probably have worked out the current population as an approximation for the year 2020, but I didn't. Here's the graph I got when I plotted those data points. So these blue dots are the data points from the previous slide. Horizontal axis is p, vertical axis is dp dt over p. I just plotted the points, that's all I did. Then I added a regression line. Straight line, this red line that follows the trend. It's approximately linear, though it's not exactly linear, certainly. There is a pattern to the residuals, and it has an effect on how well this model does, and it doesn't do a great job here in more recent years. There is a pattern to the residuals that they're positive over here, then they become negative in here, and then become positive over there. And that means a linear model is actually not the best thing. Now I could try to modify this, I could try to use a quadratic model, but what I ended up doing in a later slide is I ended up just sort of ignoring the older data from the 1790 and the 1800s and the early 1900s even, and I only focused on 1950 to the present, and I got better results that way. This red line is not something that I computed by hand. I had Mathematica do it for me. Okay, so Mathematica calculated that expression as the equation of a line as a function of p that is the best linear fit for these data. So it's approximately linear, or is it? I sort of jumped the gun on that one. It's not going to do the greatest job, but we'll see how it turns out here. So here's where I want to estimate K and L. So again, from the previous slide, dp dt over p is approximately 0.03179693 minus 0.0000994917. This thing is the K, and this number, I forgot my P, the number in front of the P there is the K over L. So, K is about that, K over L is about this, and I can now solve that system of equations for L. L's got to be this number divided by that number. Why? If this is K over L, I can just multiply both sides by L, and divide both sides by that number. L is going to be K over 0.0000994917. And K is the 0.0317693. So L is about 319.3 million. That is what this is predicting for the carrying capacity of the United States. Now, if you follow the news about population at all, you should look at that and say, that probably doesn't seem right. After all, let's go way back here. In 2010, it was 309 million. 2020 here, we could be already at 319 million. How well does it do? It doesn't do very well in recent years. It does pretty nicely at the start. But once we get to around 100 years after 1790, or around 1890 or 1900, then the logistic model is too high compared to the reality. And it also turns out that it's leveling off too soon here in recent years. And giving now estimates too low. The year 2020 is going to be one more dot, maybe about there. The red curve is going to be below it. So it does well at first, but not so well in the long run. What's the problem? We should probably not start way back in 1790. Things were just too different back then. Life was too different. Birth rates were too different. The last 70 years is probably a better thing to use. Here's the data from just the last 70 years. Once again, the instantaneous relative rate of growth versus the population itself. You don't see time in here, though. These do come in the order of the years because the population is growing over time. This is 1950, this is 1960, this is 1970, 80, 90, 2000. Yeah, and I had to stop at the year 2000. So I got a different equation there. And this does do a better job in more recent years. And what is it predicting for the carrying capacity? It's predicting about, if you look at this green line here, turns out that's about 58 million or 59 million or something. All right, 457 million. That's a horizontal asymptote. Is this going to be perfect? For sure, no. Is it reasonable? Perhaps, at least for the short run. But actually, I did, 20 minutes before class, just look up the current population and compare it with this model. And this model ended up being a bit too high. The next blue dot is a little bit lower than the red one. It ends up being too high for these numbers. So probably the carrying capacities maybe a little bit lower. It's a simplistic model, right? You're just sort of hypothesizing the existence of carrying capacity. Maybe that's a bad hypothesis. Maybe there is no true carrying capacity. But it does give probably fairly decent short-run predictions over the next 20 or 30 years. I would not use it for the next 100 years. So this is what I was having fun. I was feeling God's pleasure, in joy of doing this and trying to do something useful, you might say. I might try to modify the model to see if I can make it more accurate, but that's enough for me. What should you know about this? You should certainly be able to work with the logistic model in terms of just understanding what I've told you about it as far as the growth rates initially. When p is small, this is close to 1, and so it acts like an exponential growth. That's one thing to emphasize. Also, when p is close to L, this is close to 0. And that means overall dp dt gets close to 0, and the functions have graphs that level off. You should know what the graphs look like. And if I give you a formula, you should be able to check that it's a solution, though those end up being kind of complicated with this example. All right, for the rest of lecture A, and this will carry over into lecture B, we want to go back to doing some theory. I mentioned right the day after exam 2 that I wanted to do the theory naturally, and we have to some extent within our discussion of the applications. But I do feel like it would be good to try to summarize it all right now. So I've had you read section 3.10. Whether you did the reading or not, I don't know. I do want to read. That does definitely help prep for class and help you review things. The mean value theorem. Well, mathematicians, when they hear the mean value theorem, they start chanting, MVT, MVT, MVT. Why? They're so excited for one thing. Why? Because many mathematicians think of the mean value theorem as the most valuable theorem. That's not its name. Its name is mean value theorem, but it's super valuable to pure mathematicians, at least. Most valuable theorem. Some of our optimization facts, for example, the first derivative test, are based on the mean value theorem. And the first derivative test is certainly plenty useful. So the mean value theorem is kind of abstract, but it's got useful consequences. Here's a statement. This is the official statement. It's probably worth writing these things down. And as you write, think. This is abstract. We're supposing we've got just some arbitrary function that's nice. It's continuous, no breaks in its graph, over an entire closed interval. When you write this, A and B, A is the left endpoint of the interval, B is the right endpoint. Visually, it's all the numbers between A and B, including A and B, including the endpoints. A shorthand for this that you'll see is that x is between A and B. A is less than or equal to x is less than or equal to B. Technically speaking, if I'm going to describe this as a set of points, I should use curly braces. This is not Mathematica curly braces. This is set curly braces. The set of all points x such that this vertical line means such that, it's just an abbreviation, this condition is true. A is less than or equal to x is less than or equal to b. It's implicitly assumed here that A is less than B. Right. So f is continuous on such a closed interval. We also assume f is differentiable on the corresponding open interval. This is not a point. These are not coordinates of a point here, even though it looks like it. These, in this context, represent endpoints of an open interval. Visually, it's all the points between A and B, excluding A and B. So I put like open circles there. With inequalities, you could use a shorthand to say A is less than or X is less than B. Notice these are strict less than, this is less than or equal to's. And with set builder notation, you can write this as the set of all numbers X, such that X is strictly between A and B. But you can always just think about the picture too. So abstract, no formula for f, just properties it satisfies. Based on just these properties, you can say there exists a number c. This funny looking epsilon type symbol is a symbol for is an element of. C is an element of. Or just is in, for short, this open interval from A to B. There's some number strictly between A and B, where that equation right here is true. F prime of C equals f of B minus f of A divided by B minus A. Now when you see these symbols in this equation, alarm bells should go off in your head, or light bulbs or something. I've seen those symbols before. That's a derivative. It's a slope of a tangent line. That's a rise over run, perhaps? Yeah, it's a slope of a certain secant. The mean value theorem is telling us there's a certain point where the slope of the tangent equals the slope of the secant. Let's draw a picture. Illustrate the geometric meaning of this theorem over here. F is a nice continuous function over the interval from A to B. Maybe it's defined outside the interval as well. Maybe not. It's continuous and differentiable. This quantity here, f of b minus f of a divided by b minus a, is a slope of the secant line between the two endpoints of the graph. This point is a comma f of a. This point is b comma f of b. As a number, f of b is here, and f of a is here. So this distance right there, that's f of b minus f of a, and I've drawn it to be a positive difference. But the function could go down, and that could be a negative number. And then the rise would be negative. And this distance right there is b minus a. That ratio is the slope of that secant line. The secant line has slope equal to change in y divided by change in x, rise over run. The theorem says there's a number c between a and b where the slope of the tangent line equals the slope of the secant. Now if you look at the picture that I drew, there's more than one such point. There's a point, a number c right about here, I'll call it c1, where the slope of the tangent is the same as the slope of the secant line. Those are parallel lines. There's another point, maybe right about here, where the slope of the tangent is the same as the slope of the secant. And there's a third point, right about here, where the slope of the secant is the same as the slope of the tangent. So for this particular graph, there's 3 c's that work. But in general, you might just have one value C. Do we believe this theorem is true? Pictures can help you believe it. I can visually see there's 3 tangent lines that have the same slope as that secant. So pictures can help you believe it, but those are not proofs. Examples can help you believe it, though examples are not proofs either. Let's do an example. The point of the example is just to illustrate the truth of the theorem, not to prove it's true, but to help you believe it. An example with a formula. F of x maybe is a quadratic. X squared plus 4x, maybe minus 32 or something. That's a quadratic. Its graph is a parabola. It's going to look about like this. I made it so it's possible to factor as x plus 8 times x minus 4. Its x-intercepts are at 4 and negative 8. And that's not a very good drawing. 4 is there. Negative 8 would be about here. Those are the x-intercepts. What interval am I talking about? I can pretty much talk about any interval that I want. Maybe let's let A be negative 6 and B be positive 6. So now I'm just focused on this piece of the graph right here. Like that. I'm sort of ignoring the rest of the graph. The mean value theorem applied to this piece of the graph on this interval from A to B, negative 6 to positive 6, says there's some number C where the slope of the tangent is the same as the slope of the secant. Let's find C. First, let's find the slope of that secant line. F of B minus F of A divided by B minus A is F of 6 minus F of negative 6 divided by 6 minus negative 6. F of 6, I'm going to get 36 there, plus 24 will bring us up to 60. Double check with B. Minus 32, that'll be 28 for F of 6. That can't be right. Oh no, okay, maybe it is. I was thinking it was this one. F of negative 6 better be negative. Negative 6 squared is positive 36. Minus 24 is positive 12. Minus 32 is negative 20. Six minus negative 6 is 12. The top becomes a 46. 46 divided by 12 is the slope of that secant line. That's the same as 23 over 6. What value of C has the same slope for its tangent? I can solve for it. I can find the derivative. 2x plus 4. Set this equal to the slope of the secant line, 23.6, and I can certainly solve for x. And whatever x is will be the value of C. 2x will be 23 over 6 minus 4. 4 is 24 over 6. Right? And so this will give me negative 1/6. So x, which is going to be really C, is going to be negative 1/12. C is negative 1/12. So I've not made a mistake, at least. That's the value where the slope of the tangent is the same as the slope of the secant. Now I'm not drawing it perfectly, so it's hard to say. Does that look right? Does anybody see any mistakes? I may have made a mistake. I hope I didn't. Let me just double check things. F of 6 is 36 plus 24. is 16 minus 32. Oh, I did make a mistake. I said 28. So I get 48 over 12, which is 4, actually. Sorry. Hey! C is simpler. C is 0. I thought that might be a mistake, because with quadratics, the C is supposed to be halfway between A and B. It doesn't work that way with other functions like cubics or whatever. Don't be bothered that I didn't call it C until the very end, okay? The value of x where these slopes are equal is going to be what we're calling C. Let's take our break right there.